people, I'm Bharat Acharya. Welcome to our new video. So today in our COA course we are doing this highly requested topic, comparison between a CISC processor and a RISC processor. Now the reason why students have been requesting this so much, yes, is because you've been seeing it in every exam. Whether you're talking about competitive exams, placement exams, interviews, etc. or even your college exam in your subject of COA, this is a highly repeated question. It comes as a big distinguish. There are lots of points. Even in multiple choice questions, each of these points can be a question by itself. Now why is this so important for a student to know? If you're learning processors, you need to understand what is the thought process behind making a processor. These are two, CISC and RISC are two ideologies. Some processors are created for flexibility, like the one that is there inside your home, in your home PC, in your computer. That processor has to handle a variety of tasks. Surfing the internet, shopping, printing, playing movies, songs, and so on. So here, the kind of instruction set that you need has to be tremendously flexible to handle all these kinds of operations. On the other hand, think of the processor that manages your car, that manages brakes of your car, or the air conditioner of your car, or the airbags, which has to just detect a collision and immediately open the airbag. Now these processors don't have to do a variety of operations. All the operations that I told you about, they don't have to do that. These are designed to do a particular task. So the instruction set and the architecture on which they are created is far more rigid. But in that rigidness, you get tremendously high performance. The reaction time of the processor that handles the airbag or the traction control in a car is very low, and a slow processor over there will make the difference between life and death. So over there, more than flexibility, performance is given priority. So based on that, like I said, there are two different ideologies. That's what is RISC and CISC. I'm going to give you real world examples. I teach microprocessors, I teach microcontrollers. There are several RISC processors that I teach, there are several CISC processors. So I'm going to give you actual examples of those processors and make you understand which method fits best with which kind of processor. Okay, so the first thing, as a comparison, the main definition, CISC stands for complex instruction set computers. RISC stands for reduced instruction set computers. I'm not writing the full text, it's there in the PDF, just click the link, it'll open. I don't want to waste your and my time by writing full sentences on the board. Now, what does this mean? When you say a reduced instruction set, I'm talking about RISC, many people get a wrong idea. Reducing instruction set doesn't mean eliminating operations. It's like a CISC will have an add and subtract and RISC will have only add. No, it's not like that. It'll also have add and subtract. Then what makes you say that it's a reduced instruction set? There are very few ways of doing the operation. When you talk about CISC, CISC is flexible. Its approach is to make a flexible processor. So when you say add, there will be several types of adds. There will be add register and a register, register and a number, register and a memory location. Now when you say memory location, if you learned addressing modes, that memory location can be given using direct addressing, using indirect addressing, and so on. So you want to do add, there are 10 ways of doing it. What does this give you? Flexibility. That's the next point. Flexible instruction format, flexible method of doing operations. In RISC, you want to do add? Yes, add. But you don't have so many options. Add, subtract, multiply, divide, and, or, XOR. All of these operations are there in a RISC processor. Of course, without that, how will a processor work? But they mainly support only register-based operations. You want to add two registers? Great. You want to add a register and the contents of a memory location? No, not allowed. And what do? First take the memory data into some register, then add the registers. So your add will have only one type. Subtract will have only one type. So here where you have 5-6 types of adds, you have one type of add, one type of subtract, one type of multiply. So your overall instruction set becomes very small. That's the meaning of RISC. It is not like it has less types of instructions per se. The operations are the same. Whatever add, subtract, multiply you do with a CISC processor, you can do with a RISC processor also. But the flexibility of operands is less. So what do you get by this rigidity? You get faster performance. When you say, I'm doing add B, C, let's say B and C are registers, I'm doing add B, C. Now if you evaluate how this operation will be performed, B and C are two registers present inside the MUP, inside the processor. Addition will be done by the ALU. ALU is also present inside the processor. So the whole operation is internal, so will take one cycle. Standard, one cycle execution time. But if you say you want to add B, with the contents of memory location 2000. This is also add. Ideally this should also take one cycle, but it won't, because here inside the processor you have B register, but you don't have contents of location 2000 inside the processor. You will have to go to the memory, get the data of location 2000, then add it to B. Do you understand this will take more time to execute? Do you understand this will work slower? But it gives you the flexibility to directly add a memory operand. So something like this is allowed by a CISC processor, but is not allowed by a RISC processor. A RISC processor says first get the data into a register. Whatever data you want, get them into registers, do all your programming only using registers. So the advantage of doing that is you can be sure that every instruction will take the same amount of time to execute, same number of cycles to execute, whereas in a CISC processor, add may take one cycle, add may take two cycles. Do you understand? If both of them are memory operands, you have to get both operands from the memory, then add them, and if the result also has to be stored in the memory, again store the result back in the memory. So much more time than actually adding you are spending in getting the operands and putting the operands back in the memory. So the execution time of add will not be fixed. It will depend upon what kind of operands it is. Whereas in a RISC processor, all instructions will execute in one cycle. So because of that fixed execution time, there are more benefits that will come later. Keep watching, keep watching. So the next point continues with the same. It has more addressing modes. Since add can work with a register also, can work with a memory also. In memory it can work with direct addressing also, indirect addressing also. If you learn more of addressing modes, indirect addressing modes have so many types: register, indirect, register, relative. Remember in the addressing modes video we discussed. So you need lots of addressing modes. In a RISC processor, you have very few addressing modes because most of the work will be done using registers. Continuing with the point again, this is a logical flow. These points form automatically. Once you get the idea that a CISC processor allows variety of ways of doing the same operation, but a RISC processor restricts that. Once that idea is there in your mind, the points flow. This is more memory based, like you understood. Operations can directly work on memory. So your instructions, if you take a printout of your program, most of your instructions will be memory related operations. Whereas in a RISC processor, operations are register based. You're more dependent on registers as compared to memory. The only thing you do with memory is basically load and store. Many textbooks write this sentence: RISC processors are based on load store architecture. Now students don't understand what does this mean. Load store architecture means the only operations allowed with memory are a load and a store, which means get data from memory, send result in memory. Don't do add, subtract directly with a memory operand. No multiply, no divide, no increment. Look at this instruction. Increment B. Simple instruction will increment the value of B register. So simple. B will become B plus 1. B is a register present inside the processor. One cycle, job done. But the same thing when you say increment the contents of location 2000. Boom. This will take so much time because you want to increment a value which is not even there in the processor. So first thing the processor will have to do is go to the memory, get the data, do the increment, store the data back in the memory. Imagine in the next instruction if you're doing move CL or some register, comma square bracket 2000. Again you're going to the memory getting the data. Again you're wasting so much time going back and forth. But a RISC processor says don't work like this. Memory based operations will not be allowed except for just getting data and storing data. No arithmetic logic operations on memory. So what do? You get the data from the memory once. You do all the operations you want to do on that data using your registers. So no memory operations. And again, the only time you'll again use memory is to store the result back in the memory. So the operations become register based. RISC processors are more dependent on registers as compared to memory. So these are memory based processors. These are register based processors. Since they are memory based processors, they typically require very few registers, like 8085, 7 registers, 8086, 8 registers, all the way up to Pentium. It's just those registers become bigger in size, but it's just handful of registers. As compared to RISC processors, a PIC 18 has 4000 registers. Many ARM processor, 37 registers, much more as compared to what you get as 4 or 8 registers in a CISC processor. So the advantage of having so many registers is whatever data you want to work on, get your data in the registers, do all processing only based on registers, the operation will happen tremendously fast, and then store the result at the end back in the memory. So they need more registers to play with. These need less registers because you're more based on memory. So what is the effect of that? The effect of that is clearly shown in pipelining. What is pipelining? Define. In the simplest form, what is pipelining? Executing the current instruction while fetching the next instruction. So while you are executing one instruction, side by side you're fetching the next instruction. If you look at 8086 pipelining. So we drew the pipelining timeline like this, if you remember. Fetch one instruction, while executing one, fetch the second, while executing second, fetch the third, and so on. Remember, we overlap fetching and execution. Now a picture like this is not how it will truly happen for a CISC processor. Why? When you're saying you're executing an instruction, pay attention, you are saying side by side you're fetching the next instruction, correct? To fetch an instruction from the memory, you need buses, correct? If your execution is an instruction like increment B, where you're just incrementing a register, the register is already inside the microprocessor, it will get incremented within the processor, it doesn't need the buses. So during that execution, you can fetch the next instruction. So this image holds true, but only for an instruction like this. Change the picture. Disaster. An instruction like this, or even a move or an add or whatever where you are involving memory. While you are executing this instruction, you want to get the contents of location 2000. While storing the result, you want to store the result at location 2000. Both cases, you require the memory. To access the memory, you require the buses. If your buses are providing you this data, then how can you expect to do fetching at the same time? At this time, there will be no fetching taking place. That means there will be an empty cycle over here. When you finish your execution, here fetching of 2 will take place. Then while executing 2, you will fetch the third, which means there was an empty area. Your pipelining suffered. Your imagination that every time you're executing an instruction, you will be able to fetch the next instruction will not be necessarily true whenever you do a memory-based operation. And a CISC processor mainly does memory-based operations. So pipelining takes a very bad hit in a CISC processor, but this doesn't happen in a RISC processor because RISC processors work on registers. They are present inside the MUP. While you are executing the instruction, you have nothing to do with the buses. The buses are absolutely free. The only 2 instructions where interference of execution and fetching will happen is when you do a load and store. So other than getting the data from the memory and storing the data to the memory, the result back to the memory, all processing, all your execution will not interfere with fetching, giving you picture perfect pipelining. So it gives excellent pipelining, which simply translates to very high performance. These are high performance processors, but they are rigid because there's only one way of add. If you have to add a memory operand, you need 3 operations. First, get the operand, do the addition, store the result back. So it gives you rigidity, but it gives you high performance. This is something I've told you many a times before also. You always have a clash between performance and flexibility. As you increase flexibility, your performance will take a hit. You make the system more rigid, you get high performance from the system. That's clearly demonstrated when you're comparing a CISC and a RISC processor. They have variable execution times. Like I said, that same instruction can take variety of times depending upon the kind of operand you have. They have fixed execution times, generally 1 cycle per instruction. Both processors that I mentioned about, ARM and PIC, take pride in this statement. 90%, 95% of their instructions, of the whole instruction set, execute in just 1 cycle because of that rigid structure. So, where does this become useful? You want to extract high performance, you increase the RAM, you increase the cache, you add extra coprocessors, you make an expensive circuit, you can get high performance even from a CISC processor because the collaterals are many. This increases the cost of the system but gives you high performance with flexibility. So where does this fit in a computer where you have the choice of space, cost. That's where you can get high performance using a CISC processor. But suppose, like I said, you talk about the music system which is going to be put inside a car. The cost of that is negligible in the cost of the whole car. The airbag system, the anti-lock braking system, the processor that controls temperature in this air conditioner. These are not high cost system. Here there won't be any extra RAM, there won't be cache obviously, there won't be co-processors. Here your main processor should give you the highest performance in the smallest way possible. You don't care about flexibility here. An AC doesn't have to work on the internet. An AC, or unless it's a smart thing, even if it's a smart thing, it's a small component. It doesn't have to print, it doesn't have to send you emails, it doesn't have to do all of that. So what you don't care about is flexibility as long as you can get good performance from a single processor without the collaterals. So that is where you use the idea of RISC. Where do you use this idea? In microcontrollers. All the appliances that I told you about, they don't use microprocessors inside, they use microcontrollers. So RISC is typically an architecture built for microcontrollers. ARM is based on microcontroller logic. PIC is a microcontroller. ARM is an architecture used by both microcontrollers and microprocessors, but it was invented for microcontrollers. PIC is a microcontroller, Spark, etc. They are all based on RISC, whereas 8085, 8086 and the whole lot of microprocessors that we learn, they are all based on the CISC model. Another point from our subject, flexibility means you have a variety of instructions. To have this kind of flexible instruction set, your control unit should be such that it supports so many possibilities of instructions. You cannot build a hardwired control unit for so many instructions. So a CISC processor typically uses a microprogram control unit, if you remember the comparison, and a RISC processor where flexibility is not your concern. You have small instruction set, you have few instructions, but you want high performance. That's where a hardwired control unit is more suitable. So RISC processors use hardwired control unit, CISC processors use microprogram control unit. CISC is easy to program because of its flexibility. RISC is more complex to program. You see a program of 8085 or 8086, even if you've not really learned those processors, looking at the instructions you'll fairly understand what's going on. You see an ARM program or a PIC program and you've not learned those processors, you'll immediately shut the book. These instructions, because of their rigidness, take a lot of time to understand, are more complex to program, but the performance that they yield is tremendous from just one basic processor without having extra peripherals around it. So that is in all the theoretical points. In simple terms, I meet you someday, 2 years from now, 3 years from now, we sit together, hi, hello, exchange is done. I ask you, tell me, what is the basic difference between a CISC and a RISC processor? How do you justify your thought process? A RISC processor is interested in giving you high performance without giving too much flexibility. It restricts operations based on registers, so it has fixed instruction formats. It needs less addressing modes, but it needs more registers. It will give you tremendous pipelining because execution times are fixed. All the opposite ideas for a CISC processor. A CISC processor is made for flexibility. One single operation like an add can be done by several ways, giving the programmer the freedom to handle any kind of program, but this flexibility comes at a price. Your operations are based on memory, your execution times will be variable, fetching times will be variable because instruction sizes will be different, so pipelining will suffer. The processor alone will not give you high performance. You want high performance, you'll have to add extra peripherals to increase the overall performance, which, like I said, is suitable in a microprocessor used in a computer, but not suitable for microcontrollers which are used in appliances. Okay, so I hope I've given you a clear idea what is a CISC and what is a RISC processor. See you in the next lecture. All the best.